if you want to be able to do cyclotron problems with your eyes closed, then this is the place to be. In this video, we're going to be talking about at least 2, maybe even 3 cyclotron problems to make you have the intuition and the hang of this. And here we go. The first one is the question of what kind of field should we have at CERN? Okay, so in this question, CERN, once again, is that huge super collider, and we're talking ginormous radius, like miles in radius, so that these super high velocities close to the speed of light can be reached, which create enough energy where you can actually break down particles into their constituent parts and then actually take pictures or at least have evidence of those particles. All right, find the strength of the magnetic field required to move a proton in an 8-kilometer, it's crazy, 8-kilometer radius. It's about 5 miles, right? At 0.99 times the speed of light, which is the approximate radius of the CERN super collider. Okay, are you ready? All right, okay, let's do this. So once again, how do we get R? Well, let's say we forget it. We just remember that force equals ma. In other words, QVB must equal mv squared over r. V's cancel. Okay, so we have R equals mv over QB. Cool? Cool. All right, we want to we're talking about a proton here, right? So we're accelerating a proton so that we can smash them up together. So that means that R is going to be equal to the mass of a proton, which, as you guys know, is 1.6 times 10 to the minus 27. And we want to get this to go near the speed of light. So it's 0.99 times the speed of light, which is 3 times 10 to the 8 meters per second. Right? And then that's all divided by the charge of a proton, which, as we know, is 1.6 times 10 to the minus 19. And multiplied by, do we know the magnetic field? Do we? No, of course we don't, because that's what we're solving for. We're solving for this B, but we do know the radius, which is 8 kilometers. To keep it in SI units, I want to do 8,000 meters, right? Okay, so if we then want to solve for B, we just basically flop these. So we have B equals 1.6 times 10 to the minus 27 times 0.99 times 3 times 10 to the 8 divided by 1.6 times 10 to the minus 19 times 8,000. All right, lovely. So that, my friends, is all going to equal a B field of 3.8 times 10 to the minus 4 Tesla, which is actually a pretty decent sized magnetic field, even though it looks small. But remember, 1 Tesla is actually huge. All right, so this would be the magnetic field required at CERN to get a proton to go at dang close to the speed of light. Pretty cool, right? All right, let's keep practicing here. Let's look at this whole idea of a mass spectrometer. Okay, so a mass spectrometer is, especially if there's any of you folks who are going to go into chemistry at all, it's a really cool way of isolating isotopes. Okay, so remember this radius. I'll write this formula for the radius one more time. Radius equals mv over qb, right? The radius changes if the mass changes, right? And as we know, the isotopes of different elements will all have different masses. So if you have, so let's say you accelerate a particle, right? Or let's say some sort of like some ion with a certain mass, right? And you put it suddenly into a magnetic field, right? Okay, and as you know, there's going to be circular motion that starts to happen, right? And then whoa, eventually, if the field isn't everywhere, right, it'll come out and then it'll go in a straight line after that, right? Because there's no more field acting on it, it's not going to want to turn in a circle anymore. All right, cool. So what does that mean? That means that for any given mass, there is some radius of that circle that is going to allow us to pull this around, right? So a different mass might have a radius that looks like this, right? So if I have different little containers here, a container here and a container here, then I can get one isotope to fill up this container, right? Because that's one certain mass with one certain radius, right? And then another mass, another isotope with a different radius, I can collect it over here in this little container, okay? So it's this really clever, kind of beautiful way of actually being able to isolate isotopes, which has certain applications in material science. And one really huge application is when scientists were working on the Manhattan Project, which was the World War II project when we developed the atomic bomb for the first time. And in order to do that, you need a very specific isotope of uranium, which is uranium-235, because it's easier to form a chain reaction with that isotope, okay? So we had to collect a bunch of that isotope. We had to mine uranium and then use this process to separate the different amounts, also known as enrichment. You maybe have heard like enriching uranium, like you heard it in the news. So this is that process, okay? So here's the question. If a mass spectrometer fired uranium atoms, which are +1 ions, at a speed of 400,000 meters per second through a 500 millitesla magnetic field, how far would you have to put a lead vessel to capture that 235 isotope? Okay, all right. So not too tricky here. We're talking about uranium atoms, right? So uranium, it's 235. So there's going to be 235 protons and electrons, all right? And they each have a mass of 1.6 times 10 to the minus 27, right? And we are firing them at 400,000. So I'm just going to put this through here. 400,000 meters per second. Okay? And the charge of each one is a +1 ion, so that's 1.6 times 10 to the minus 19, right? And the B field, they say, is 500 millitesla. So that's going to be 500 times 10 to the minus 3 teslas, all right? So that means that the radius of this circle, right, is going to be, according to my calculations, 1.88 meters. Is that our answer? No, because one radius would only get you here. We want to get all the way back over here so that we can collect it in our little container. So we actually need two radiuses, or one full diameter, which if I double that, I get 3.76 meters. Okay, so I can basically fit this in a room. I have this mass spectrometer that I put in a room, have this little bucket over here, 3.76 meters weight exactly, have the proper magnetic field, put it in with the proper velocity, and I can start collecting all those isotopes to make this bomb. And now I'm realizing it's probably pretty questionable that I taught you all how to make an atomic bomb. Please don't tell anyone.